Cars capable of autonomous driving are starting to take over the industry. But how confident are we in their capabilities? Do we really trust them? Well, we don't think so, at least not yet. This is where our project comes in. Our goal was to design and build a 10-scale RC car with mini sensors that mimic those on real-size autonomous cars. The setup would serve as a test bed in testing many autonomous driving applications. I'm Omar Abbas, and I worked on designing and integrating our hardware components with software applications in our Linux-based platform. I also worked on developing our documentation site, supercomo.com.
My name is Stephen Reed. I worked on software development as well as researching and implementing the hardware in ROS.
My name is Jocelyn Ives. I worked on researching hardware components and designing the CAD files for the decks and the hardware mounts.
My name is Alvaro Spadichari. I was responsible for the microcontroller subsystem and implementing the software for reading our low-level sensors.
I'm Slimy Safawi. I'm the team leader, and I was responsible for all administrative tasks, hardware assembly, software development, and shell scripting.
Hi, my name is Ridwan Giwa, and I was responsible for the hardware components, circuit design, and record packaging. Okay, so our project is divided into three parts: the hardware components, software integration, and experimental validation. SuperComo is made unique with the multiple sensors that is integrated into the project. We have the 2D LiDAR. We have 5 cameras. We have ultrasonic sensors, wheel encoders, and a GPS, and also an IMU. All this hardware are then placed into a custom-made deck, which then feeds data to our AI embedded systems called NVIDIA Jetson TX2.
And then to perform autonomous driving features, we need the actuators, sensors, and processors all to operate together. But all of these different components have their own software packages. And so to integrate all of these different system components together, we rely on ROS, the Robot Operating System Framework. With ROS, we can manage all the different devices, transfer data between processing nodes, and issue control commands. And then we can use one file to start all the devices we want and the control pipeline.
To demonstrate our platform, we do several key autonomous driving features. Our car can do line following, where it uses cameras to detect the line and follow it. It does collision avoidance, where it stops if there's an obstacle in front of it. It does hallway navigation using the LiDAR. It traces the wall to its left. And object recognition, where it uses machine learning algorithms to detect objects and recognize them and use them in its pathway. Our final design is a powerful and reliable test bed that has over 98% success rate in the platform and well over 3 hours of operation time. Thank you, and I'd like to open the floor to questions.
How did you utilize the IMU?
So right now we're not utilizing the IMU. Not all of our applications require all of the different sensors. Nonetheless, we can operate them all together. One of the usages for IMU is potentially either detecting the tilt and rotation of the car, or even integrating the acceleration to get an estimate of the velocity, which can then be added with the encoder or fused with the encoder estimate of velocity to produce a better estimate of that.
So how many accelerometers and gyros are in that IMU?
So the IMU has one accelerometer, one gyroscope, one magnetometer, and each has 3 axes.
Okay, thank you.
Have you tested this outside?
Actually, yes.
Okay, tell me about it.
We actually do have like a YouTube video where we have it running on our hallways at ECS North. We have it running outside in the little plaza outside of ECS North. And we also have it running in our lab where we have sort of made a makeshift environment, and we just have it, do its own thing, run around, hallway navigation, line following, everything.
Did you see any differences between inside and outside, or the way it runs?
Not really. It did pretty much about the same thing and what we expected. Some of the sensors are maybe a bit deficient outside, such as the LiDAR. It operated this time really well, but some LiDARs, sometimes it doesn't work really well outdoors because of IR interference. But that's exactly why we have all this redundancy in sensors. And another reason why we have a 3D stereo camera and not an IR-based stereo camera, because those work better outdoors. We also have ultrasonic sensors because even if they are not as reliable as LiDAR sometimes, because of how weird they are in terms of detection, they still operate better outdoors than the LiDAR does in certain situations. And that's why we have all of these different components and different sensors to try to get as much redundancy as possible to make it as best of a platform as we can.
What kind of differences do you see in daylight versus dark?
So in terms of vision, you would probably see a bit of a difference because some vision algorithms don't work really well outdoors, especially or in the dark, especially if you don't have light. But other sensors like ultrasonics and LiDAR encoders, these don't really rely on light because they have their own emitter, so they won't be affected. So virtually, if we wanted to run, or practically if we wanted to run our hallway navigation algorithm, which essentially traces a wall to its left using the LiDAR, it would work in whatever condition you want, as long as the LiDAR can actually detect the object, which basically means like no glass.
You say that the last bullet point, 94% successful trials in different environments.
Yeah.
Did you get to that number from a very lower number? So successfully you went up in your success rate.
Okay, so one of the things is that we wanted to test the capabilities of our platform by demonstrating as many experiments as we want. So these individual application-based success rates probably do not affect our platform that much. The most important factor is how successful it is as a platform, because that's the most important thing. Your algorithm may be good or not so good, but if the platform fails, you won't be getting any results. So going back to your question about those particular results, we actually ran multiple experiments. We have maybe over 50 or 70 experiments for line following. We have various experiments, maybe over 50 experiments for hallway navigation. And even after that, we actually performed a 3-hour-long demonstration where the car was running this hallway navigation, and it ran fine all the way through. So really happy with the results we got, and really confident, and we think that we can that the actual results are even higher than these success rates.
Thanks.
All right.